Hi, so this is our second video on functions of a random variable. This time I have a new distribution. We're going to let x be a uniform and y is the reciprocal of it. I am trying again to get the probability density function of this guy. So hopefully you're getting a little bit used to the lingo of random variables. So I'm going to let x be a uniform random variable on the interval 0 to 1. And there actually is a discrete uniform and a continuous uniform, but I know this one is continuous because you have an interval. Anytime your support is on an interval, you have a continuous random variable. It can't be defined at every single point in there, right? I mean, it's not discrete like 1, 2, 3, 4. So given that I know I have this interval, I know I have a continuous random variable. So actually, this guy is probably the simplest one to work with and to draw. So here is, put a little hole up there. Here's f of x. F of x is just 1. A uniform on the interval 0 to 1 just has a f of x of 1. Nicely, you can see the area under the curve of this guy is 1. I don't even need to integrate him. So we're working with x, who's uniform, and that's its density function, and that's its support, okay? So now, this looks like it should be an easy problem, but I want to find the distribution of the reciprocal of x. And again, I mean, you can see where if you just think, oh, I'm going to sub in, this in for that, it's just not going to work out that nicely. This is actually a tough problem again. I talked about in the other video, there are two techniques. There's the transformation technique and the Cdf technique. I really like that Cdf technique. That's my favorite of the two. So I'm going to do this problem again using the Cdf technique. So Cdf technique. Plus, I always know where to start. You start with a CDF. That's why I guess I think, oh, CDF technique. I know where to start. And if I know where to start, then I feel like the rest of this really flows from the beginning. So the CDF, I want to get the CDF of y, eventually get down to the PDF of y. So CDF technique, first I'm just going to write what the CDF of y is, which is f of y. That's just what the cumulative distribution function is. And so by definition, I'm just reminding myself, capital F of y is just the probability that y is less than or equal to little y, the area under the curve up until little y. Okay, so now like I said, I'm kind of stuck. I don't have anywhere to go, but I do know things about x, so I want to get a probability statement in terms of x. So here's always where I'm going to do my subbing. So sub y, sub for y in terms of x. So right, I have some statement over there in terms of x, and if I can get a probability statement in terms of x, and I'm working with a continuous, I'm just going to be integrating to find that formula for y. So let's do a little subbing. This is probability 1 over x is less than or equal to little y. Okay. Again, if I can just get x isolated, I can look at the integral that I would make up to then move further. So I'm going to do a little cross multiplying. So move that, right? So this will be 1 over y less than or equal to x, like that. Just because I like to look at statements, I guess, with the x on the left, that's just maybe a psychological thing. I'm just going to rewrite this. Greater than or equal to 1 over y. Same thing, right? I'm just rewriting. Okay, so I know that x is a uniform. And now I'm just trying to find the probability that x is bigger than 1 over y on the interval 0 to 1. So I think the difference for me, why I did example 10 that I did earlier in 12 here, now my support, this is going to be the lower bound of my integral. In the upper bound, since x is defined on 0 to 1, this is the lower bound, and I'm integrating to the upper bound, which is 1. So imagine, again, somewhere sitting in this 0 to 1 interval is 1 over y. To find the probability x is bigger than 1 over y, I'm going to integrate from that up to the upper value of my support for the random variable x. And again, if you get confused, just think, I mean, if this was a number like a half, you would be integrating from a half to 1. So don't let that variable mess with your mind, Okay, so let's set this up. So this is the area under the curve. The density function for capital X is 1. And I'm going from x equal 1 over y to x equal 1, and this is dx. If x had been something other than a uniform, let's say it was an exponential, this would be the density function of an exponential. If x was a normal, this would be the density function of the normal. All we're putting here is f of x dx. It just so happens we have the friendliest f of x in this example. Okay, yay, even I can do this even without maple. Here is x, x equal 1 over y to 1. So this is going to be 1 minus 1 over y, and I'm pretty good to go. I've done the hardest part. Reminder, at this point all you have is the Cdf, so this is capital F of y. And you're almost there, but just don't get too hungry for, hey, I'm done. Last step, I gotta go from Cdf now to PDF. So I want the little f. Little f is just the derivative of capital F, which is the derivative of 1 minus y to the negative 1 derivative, okay? So derivative of 1 is 0, derivative of this, bring that down, so this will be 1 times y to the negative 2, which is 1 over y squared. Interesting. I mean, I started with something that was uniformly distributed. I'm looking at the distribution of the reciprocal, and this is what the distribution of the reciprocal is. This is f of y. Last problem. The only way I'm going to know if he's valid is to know what his support is. And this is a little bit tricky. So here, I'm sure of this part. Now, x is defined 0 to 1. So x's are defined on 0 to 1. And y is equal to 1 over x. So if I look at the picture, 1 over x, where can I put it? Here's the graph of 1 over x. Let's just put it really here. And I'm looking at the interval 0 to 1. So for x's from 0 to 1, y's go from here to there. At 1, actually, I get 1. So it looks like for x's between 0 and 1, my y's are going from here to there. So y's are actually going from 1 to infinity. So down here, my support is y bigger than 1. So there's my density. There's my support. If you want to check me, go ahead and integrate this guy. You'll see the area under the curve of 1 over y squared, y bigger than 1 is 1. So he's a legal density function. Everything is nice now. Again, I like this technique a lot, the Cdf technique. So now you have two videos. They're both a little bit different. They have a little bit, start with different density functions, but I hope that you're getting the feel of how these, how I'm developing the PDF. If you want to see another video, now that I have help and somebody that can help me make these, I can do a couple more for you this way. But please let me know if you like this, because we're going into joint distributions, and I can do these board examples if it's helpful. So, okay, thanks. Have a good weekend.